Hi everyone, welcome back to Chem Help ASAP. Today we're going to be talking about entropy. Let's get started. Entropy is a thermodynamic function, specifically a state function, and it describes how energy is distributed among the energy levels and the particles that constitute a given system. I know this sounds very complex, so let's break it down a bit. Entropy is related to the number of microstates of a system. Now, a microstate is just a specific configuration of that system. Generally speaking, as the number of microstates increases, the entropy will also increase. So you'll have a delta S value that will be greater than 0. It'll be positive. As the number of microstates decreases, the entropy will also decrease, and this will give you a negative value for delta S. The system with the most microstates, or the greatest number of microstates, is going to be the one with the greatest entropy. Now, when you have many microstates, what it also produces is disorder. So it will also be the system that is most likely to have disorder. But I think entropy makes a little more sense if we can connect it to something that is in our everyday life. So imagine a deck of cards. You can have two different states for this deck of cards. You can have an ordered deck of cards. So maybe you've put all of the aces together and the twos together, etc., etc. Or maybe you have ordered it such that all of the suits are together. There are certainly multiple ways that you can have an ordered deck of cards, but then I want you to compare that to a disordered deck of cards. How many ways can a deck be shuffled? And there are so many more ways that you can have a shuffled deck versus an ordered deck. This is what we mean by how many microstates you have. An ordered deck has a few number of microstates, and a disordered deck of cards has many microstates. What this means in terms of entropy is that your ordered deck of cards is going to have less entropy than your disordered deck of cards, which will have greater entropy. So while entropy isn't disorder specifically, it's very closely tied to it. So now let's consider different processes and see what the change in entropy is for that specific process. Let's take processes that increase entropy or will give us a positive value for delta S. Obviously, this list I'm going to give you is not exhaustive, but hopefully should cover the major types of processes that you will see. Starting with melting. So this is a solid to liquid transition. There are more microstates for where the particles can be when that substance is in a liquid form, or you can think about how in a liquid form the particles can move around more. Or you can think about how in a liquid form there's going to be more disorder of those particles or those atoms or molecules. So that is a process that increases entropy. It's a positive delta S. The same is true for vaporization. So going from a liquid to a gas, again, the molecules or atoms or particles have even more space to move. There's more disorder. So again, that is a positive process for entropy. Our last phase change, solid to gas. Again, you're going from a very ordered state, the solid, into a very disordered state, the gas. That is going to increase entropy. In general, increasing temperature is going to increase entropy because, again, if you think about heating up a gas, you give those particles more energy and that will increase entropy. So that is, again, a positive delta S. Dissolving a solid into solution. Again, you take a solid, which tends to be fairly ordered, and you put it in solution where the particles can move around. So this would be salt dissolving in water. And finally, any reaction that increases the number of microstates, which again will increase the disorder. So for example, consider this reaction. We start with a solid, a very ordered substance. We do form some solid, but we also form some gas, which is very disordered, or you can think of that gas as having many microstates, more microstates than a solid would. So we go from an ordered state to a less ordered state. That is going to increase entropy. Now let's take a look at some processes that will decrease entropy or will give you a negative value for delta S. Going through our phase changes like we did for our increase in entropy, If you freeze a substance, then you're going to a more ordered state. That is going to be a negative value for delta S. If you condense a gas to a liquid, again, you're going to a more ordered state. That will give you a negative delta S. And of course, gas to solid or deposition, you go from a very disordered state to a very ordered state. So that also is going to be a decrease in entropy. Decreasing temperature. The molecules have less energy. They're going to have fewer microstates. That is going to decrease entropy. Precipitation reaction, that's taking ions that are moving around in solution and putting them into a solid form. That is decreasing the number of microstates. That will decrease entropy. And of course, any reaction that decreases the number of microstates or disorder. So consider this reaction. While yes, you do have a solid as a reactant, you also have a gas which is very disordered or has many microstates, and you are forming a solid product with no gas. So overall, your reactants have more disorder, your products have more order, so this would be a process that decreases entropy. So finally, I want to talk about how we calculate entropy. And this is extremely similar to how we calculate enthalpy. We're just going to take products minus reactants. So hopefully this equation is familiar to you, and it does work the same way. So let's calculate the delta S for this combustion reaction right here. So here is a table giving me lots of values of entropy for different compounds. Obviously, I won't need all of these, but I have to make sure I pick out the correct ones. And I am simply going to plug into my equation up here. So for my products, I have water and carbon dioxide. So finding water right here and then carbon dioxide, and yes, they're both in the gas phase. Here is my first term for calculating my delta S. Then my reactants are oxygen and C3H6. Again, finding these in my table, plugging into my equation right here. I get a delta S of 39.2 joules per Kelvin. There are two common mistakes that I see with these calculations. The first is just reading the table wrong and grabbing the wrong entropy value for the compound you're doing. And the second is forgetting to multiply by your stoichiometric coefficients on your balanced chemical equation. I hope you found this video helpful, and thanks so much for watching.